All right, this is chapter 4, lesson 1, polynomial functions. So if you have this handout, it's going to be on this handout. Polynomial functions is on the left-hand column.
Ryan,
All right.
Did I say this wrong?
All right. So let's talk, first of all, what is a polynomial function? So we're going to talk about the definition. What constitutes a polynomial function? Well, it has to be an equation. And here's two things. Two things have to be true. The exponents have to be all whole numbers. If they're whole number exponents, then you cannot have anything under a radical. That's not a polynomial. Well, that one was x cubed. There we go. That's not a whole number exponent because that's x to the 3/2. The other one was just x. Bad example, huh? So whole number exponents and no variable in the denominator. That's the two rules. It is a polynomial if all of the exponents are positive, are whole numbers, and there are no variables in the denominator. So, I'm going to write some expressions on the board and you tell me if they're polynomials. Is that a polynomial? It is a polynomial.
Yes.
Is this a polynomial? Why is it not a polynomial? Because that's 1 over x squared, moving it to the denominator. All right? What about that? Is that a polynomial? That is not a polynomial. All right? So you get it? All right, now I'm on page 240. You remember the degrees of the polynomial. How to determine the degree? You look at the variable with the highest exponent, right? But what if I have a polynomial that just looks like that? So it look like f of x is that. What's that called?
First degree.
It's a 0 degree, but the name of it, it's called a constant. That's a constant polynomial because it only has a constant term. Why is it important for us to look at the degree of a polynomial? Brian? How many changes in direction, right? How many maxes and mins? Visually, what does the graph look like? That's what it's going to tell us. Because your first degree functions, polynomials, are all linear. Your second degrees are all, what do they look visually like? Parabolas, right? All your second degree polynomials. Your third degree polynomials are cubic. They look like that or that. Your fourth degree, so on. Quartic, actually. Second degree is quadratic. All right? So do y'all remember polynomial division? We can use polynomial division to factor. All right, so we're gonna remember long division, and then we're gonna remember. Do you remember the other one? Synthetic division. All right, so we're going to work this example, long division, then synthetic. All right, remember what I write under the dividing sign. It has to have a placeholder for every exponent. All right, so I have 3x to the fourth. How many x cubes do I have? 0x cubed. Every exponent has to have a place. I have negative 8x squareds. I have negative 11x's, then my constant. I'd always divide with the x first and the constant second. All right, so I ask myself, 3x, this is divide, multiply, subtract, bring down. Divide, multiply, subtract, bring down. Okay. 3x to the fourth divided by x is what? 3x cubed. Then I multiply. I'm distributing that 3x cubed to both of the x and the negative 2. So I end up with 3x to the fourth minus 6x cubed. This entire term is subtracted. Your first term, if it doesn't eliminate, you've done something wrong. 0 minus a negative gives me a positive, so that I have 6x cubed. I bring down the next term, minus 8x squared.
How do you know 6x cubed?
Negative 2 times 3x cubed.
Yeah, but how does that eliminate?
It doesn't eliminate. Only the first one eliminates. It's minus a negative, which is plus. I have 0 plus 6 to get 6. All right, so 6x cubed divided by x is what?
6x squared.
6x squared. That's what I'm distributing to both the x and the negative 2. And I get 6x cubed minus 12x squared. I subtract. The first term always eliminates. This is negative 8 minus a negative, which is positive, and I end up with 4x squared. Is everybody with me so far?
How'd you get the negative 12x squared? You did negative x.
So I'm distributing the 6x squared to the x, then to the negative 2. Both of these terms. 6x cubed, negative 12x squared. Got it?
Why wouldn't it be negative 12 to the x to the cube?
Because it's just 6x squared times negative 2.
Okay.
Literally, it's 6x squared times x minus 2. It's distributing. Bring down the next term. 4x squared divided by x is 4x. Now I'm distributing the 4x to this binomial. So it's 4x times x, which is 4x squared. Then it's 4x times negative 2, which is negative 8x. God bless you. So the first term eliminates. It's negative 11 minus a negative, which is positive. So it's negative 3x. I bring down the next term. Then it's negative 3x divided by x, which is negative 3. Then I distribute the negative 3 to the binomial, x minus 2. So it's negative 3x plus 6. I subtract. It's negative 5. That's my remainder. So I have remainder of negative 5 over x minus 2. All right, let's do that synthetically. I much prefer synthetic division. You can always use synthetic division. Only if you have a linear divisor. That's a linear term. All right, so you remember, what do I put in my backwards L? It's whatever makes this 0. It's whatever makes this 0, so it's positive 2. Now I write all my coefficients. Every exponent has to have a place. So it's 3, 0, -8, -11, +1. Just writing the coefficients. With synthetic division, I bring down only the first time. Then I'm multiplying, adding, multiplying, adding. I'm only bringing down that very first term, then I'm multiplying and adding. All right? So I bring down the 3. I'm multiplying what's in the backwards L times what's below this line. So it's 2 times 3, then I'm writing it above the line. That's 6. Got it? 2 times 3, write it above the line. Now I'm adding. 0 plus 6 is 6. Now I'm multiplying. 2 times 6 is 12. Writing it above the line. Adding -8 plus 12, which is 4. Now I'm multiplying 2 times 4, which is 8. -8 plus 11 is -3. My last term below the line is always my remainder. So 2 times 3 is -6. I add them, it's -5. With synthetic division, we get the coefficients of the answer. Got it? If 3 goes with x cubed, this first term here goes with 1 exponent less. So 3 goes with x squared plus 6. Wait, we started with x to the 4th, Paula. All right, we started with x to the 4th. 3 goes with x to the 4th, so this is x cubed. X squared plus 4x minus 3. Remainder of -5 over x minus 2. We get the same exact answer. You see? Same exact. Use synthetic division if you can. All right. I want to show you something else with this. We can all oftentimes know what the remainder is without even having to go through this. Let me ask you a question. If I have a remainder of 0, then what is true?
Then there will be no remainder.
There's no remainder. That is correct. Do you already know what that is? All right, so it would be x. So we have x squared plus 2x. We have a remainder of 0. When we have a remainder of 0, then we know that this times this equals this. So we factored it. So I can already know without having to do long division, is this a factor of this? And I'm going to show you how. All right? All right, so I'm going to erase this, but you get it, huh? If I asked you the question, is x minus 2 a factor of this? Then I just plug in 2 to the equation. When I plug 2, which is the solution to this, into the equation, I either get the remainder or I get 0. All right, so let's do it. I need y'all to help me. All right, what's 2 to the 4th?
64.
That's 64. Or 3 times 2 to the 4th is 64.
Well, 2 to the 3rd is 8. So 8 squared.
It's 16.
16. Wow. Wow.
Minus 8 times 4 minus 22 plus 1. All right, so do that. That's 48 minus 32 minus 22 plus 1. That's
-5.
49 minus 54 is -5. Look at that. We got the remainder. That's the remainder theorem in your textbook. That's the remainder theorem, which is on page 244. So, if you're given any two terms, you can determine whether or not that term that you're dividing by is a factor by plugging in the solution to get the result. Look at example 3. Example 3 tells you determine if 2x squared plus 1 is a factor of that. Well, we can't do synthetic division because we don't have a linear term. But if we do 2x squared plus 1 equals 0, that's 2x squared is -1. X squared, well, we can't do that because it's a -1/2. All right, we can't do it for that one. But we have to do long division for this one. All right, so you can't do long division here because it's the square root of a negative. They're imaginary solutions. All right, do you see they do long division? And they come up with factors. And the remainder is 0. All right, so look at example 3. That tells me that 3x minus 2 times 2x squared plus 1, that equals 6x cubed minus 4x squared plus 3x minus 2. Does that make sense? Make sense? All right, look at example 4. We're going to use this to completely factor polynomials. All right, it says find the remainder, and so we would never try to factor this when it's divided by x minus 1. Well, you never do that, would you? It's too big of a numbers. Okay, too big of exponents. But what am I going to plug in to the function? +1. What's 1 to the 79th?
1.
What's 3 times 1 to the 24th? And that gives us a remainder of 9. So is this a factor of that? The answer is no. Does that make sense? All right, let's jump to example 6. So on the bottom of page 245. Now it says show that x minus 3 is a factor of x cubed minus 4x squared plus 2x plus 3. Can I do that? Yes. I can plug f of 3 into this function. So that's 3 cubed minus 4 times 3 squared plus 2 times 3 plus 3. Isn't 3 cubed 27? That's 9 times 4, which is 36. That's 6. That's 3. Does that equal 0?
Yep.
Okay, watch what I can do. I can figure out what x minus 3 times what equals that by doing synthetic division. So if I do synthetic division, it's 1, negative 4, 2, 3. I know I'm rushing. I'm trying to get through the lesson. I bring down, I multiply, I add, I multiply, I add, I multiply, I add. When I get a 0, then I know that x minus 3 times x squared minus x minus 1 are the factors of that. And then, could I get all the x-intercepts? Yes! Because I have a first degree, I know my x-intercept is 3. And what could I use to find the x-intercepts for this one? It's actually going to be imaginary, but I could use the quadratic formula, right? And I've already done that in my book. It's 1/2 plus and minus. When you use the quadratic formula, it's 1/2 plus and minus square root of 5 over 2, I believe. So I could find all my x-intercepts. By using the factor theorem. This is the factor theorem. Once I plug in that, I know that it's a factor. If I don't get 0, then what do I know? That's the, say it, remainder. And it's not a factor. So once I know it's a factor, I can do synthetic division. And instead of having an x cubed, I now have a linear term, and I have a second degree term. And I can go, and that's what I want to do. I want to continue using synthetic division to get it to a second degree term to completely factor it and get the original polynomial and get all my x-intercepts. All right, so look at example. I want to jump real quick to 8. And then we'll go back to 7. All right, it says find 3 different polynomials of different degrees. And here are the zeros. 1, 2, 3, and negative 5. Those are the zeros. When I say those are the zeros, what do you know they are? They are x-intercepts. They're solutions. It's where it crosses the x-axis. Or it at least touches the x-axis. All right? So I can come up with different polynomials. In order for this to be an x-intercept, the factor has to be x minus 1. You connecting that? In order for that to be a 0, that has to be the factor. In order for this to be a 0, the factor has to be that. In order for this to be a 0, that has to be the factor. In order for that to be the 0, that has to be the factor. Okay, I could come up with different polynomials. I could square this term, I could cube that term. I can make that one to the 5th degree, that one to the 4th. You know how you can come up, there's infinite possibilities for the polynomial, right? Okay, the degree, if this was my factors, the degree of the original polynomial would be 2 plus 5 plus 1 plus 4. Got it? That would be the degree of the original. So the number of zeros is dictated by the degree, right? All right, let's just back up to 7. And 7 wants us to find the x-intercepts of this. They graph it. And they do second trace 0. All right, so I'm going to write what the zeros are. After they graph it, that's their zeros. So A and B are both the x-intercepts and the zeros. Same answer. C says, what are the solutions? That is the solutions. Can we write the factors from this? Yes, we can. So what would the first factor be?
X plus 3.
X plus 3. What would the second factor be?
3x plus 2.
3x plus 2. So initially, actually,
Is it 2x plus 3 right now?
minus. Initially, it would be x minus 2/3, right? But your 3 comes out front. All right. And what's the last one?
X minus 12.
Here's what has to be true. When I multiply all the first terms, I have to get the first term. X times 3x times 5x gives me 15x. How do you think I get the constant? When I multiply all of the constants, I have to get positive 72. That's negative 6 times negative 12 is positive 72. So if I give you an equation that says 5x to the 5th plus 6x squared minus 3, what are the most maximum number of zeros that we have?
7. Or wait.
5. The degree, the highest degree. Got it? All right, so this lesson is all about polynomials and zeros and how we get them.